Welcome to The Deep Dive, the AI Paper Podcast. We're here to break down the key ideas from really important machine learning research, making it, easy to grasp. Today we're tackling a big one, a really practical problem in building specialized LLMs. How do you actually pump in domain knowledge without, accidentally breaking the model? We are diving into a paper called The Knowledge Infusion Scaling Law, Avoiding Memory Collapse in LLM Pretraining. And hey, for those short on time, here's the rundown in about a minute.
Okay, so large language models, LLMs, they're fantastic generalists, right?
Yeah.
But maybe you need one that's an expert in, say, biochemistry or, maritime law. You have to inject that specific knowledge, usually during pre-training.
But here's the kicker. Training these things costs a fortune. We're talking potentially hundreds of millions of dollars. You can't just guess how much specialized data to add. Inject too little, and your model isn't really an expert. Inject too much. Well, this paper shows what happens then. And it's not pretty.
Yeah, they pinpointed this thing called the memory collapse phenomenon. Basically, for any given model size, there's a limit, a threshold. If you keep adding knowledge frequency past that point, the model doesn't just stop learning. Its ability to retain that knowledge actually tanks. It sharply degrades.
Right, you end up making it forget stuff by trying to teach it more. And the really weird part, this collapse point isn't fixed. It changes depending on the model size, but maybe not how you'd expect.
Exactly. Larger models, the big ones, they actually need proportionally less knowledge infusion to get saturated. They hit that collapse point much, much earlier.
So they learn faster, but they also break faster if you overload them with repetitive facts.
Which leads to the solution they proposed, the Knowledge Infusion Scaling Law. It's essentially a predictive formula. It lets you figure out the optimal, most cost-effective amount of domain knowledge to inject into a huge LLM, just by looking at results from much smaller, cheaper models first. Saves a ton of guesswork and compute power.
Okay, that's the big picture. Let's dig into how they actually set up the experiment to figure all this out. For our listeners, especially the ML engineers tuning in, understanding these research variables is pretty crucial if you want to apply these ideas. So why even bother developing these predictive scaling laws? Was it purely academic?
Oh, not at all. It's driven almost entirely by economics. Like you said, training these models costs staggering amounts of money. It's just not feasible to do trial and error anymore. You absolutely need a way to predict how things will scale. You want to maximize both things, memorizing the special stuff and not forgetting the general stuff efficiently.
Makes sense. So the study looked at three main things they could change. What were they?
Right. So first up was model scale, which they call non-dollar. They didn't just test one or two sizes. They used 7 different ones, ranging from 137 million parameters, which is relatively small these days, up to 3 billion.
Okay, a decent range. What was next?
Second was training tokens, dollars. They used a filtered version of the FineWeb ADU corpus. They ran experiments with 58 billion tokens initially, then later expanded to 75 and 100 billion. And a key point here, they were super careful filtering it to make sure none of the evaluation data accidentally leaked into the training set. That's critical.
Right, you need to know the model learned the facts because you injected them, not because it saw them somewhere else. And the third variable, that sounds like the crucial one.
Yeah, knowledge frequency, $5. This was basically their control knob for how much knowledge they injected. They varied the number of times each specific knowledge fact or triple appeared in the training data, from just 10 times all the way up to 10,000 times.
10,000 times.
Yeah, a huge range. But they needed that sweep to really map out the whole curve, from not enough infusion, finding the sweet spot, and then pushing it deliberately into that collapse zone.
Okay, and where did they get the knowledge to inject? You mentioned triples.
They used Wiki Data. They randomly sampled factual triples from it. Things like Statue of Liberty, location, New York City, or water state liquid.
Why Wiki Data? LLMs see tons of facts during general pre-training, right?
True, but Wiki Data is especially good because it's packed with more specialized, kind of niche, long-tail facts. The sort of stuff that a model trained just on the general web might miss, or worse, hallucinate about. It's exactly the kind of knowledge you'd want to inject for specialization.
Gotcha. And they couldn't just feed the raw triples like bottle material, glass, into the model, could they?
No, exactly. They converted these triples into natural language sentences. Things like, the material of a bottle is glass. They used a few different templates to phrase the facts. And then they mixed these fact sentences into the main training corpus at those varying frequencies to $5.
Okay, that covers the setup. How did they measure if the model actually learned and retained these facts? The evaluation part sounds tricky.
It was pretty rigorous. They used a separate set of over 28,000 unique Wiki Data triples for testing, none of which were in the training injection set, obviously. And instead of just asking an open-ended question like, what is the material of a bottle? Which can be hard to score reliably.
Right, the model could say something plausible but wrong.
Exactly. So they used a multiple choice format. They'd give the correct answer, say glass, along with several plausible wrong answers like plastic, metal, wood. Sometimes they even used GPT-4 to help generate really tricky distractors.
Clever. And how did they determine the model's choice? Not just accuracy.
They used Perplexity, PPL. This is maybe a bit technical, but it's important.
Let's break it down. Why PPL?
So PPL measures how surprised a model is by a sequence of text. A lower PPL means the model finds the text more probable, more predictable based on its training. They calculated the PPL for the sentence completed with the correct answer versus the sentences completed with the distractor answers. The option that resulted in the lowest PPL was considered the model's answer.
Ah, okay. So it's not just about whether the model can generate the right word, but how confident it is, how deeply that fact is embedded in its parameters.
Precisely. It's a much finer-grained measure of actual parametric memorization, not just surface-level generation. It tells you if the knowledge is really baked in.
And using that precise measure led directly to seeing this memory collapse phenomenon. Right? Describe that curve they found. It sounds pretty dramatic.
Oh, it is. If you plot performance knowledge retention against the injection frequency, $5, you see this really clear pattern. At first, as you increase $5, performance shoots up. Repetition works, the model learns the facts better. Makes sense.
Okay, standard learning curve so far.
Right. But then it hits a peak. And after that peak, if you keep increasing the frequency, the performance doesn't just level off. It falls off a cliff. It degrades sharply.
Yeah.
And in some cases, especially with the smaller models pushed really hard, the retention actually dropped below the baseline, below a model that got 0 injected facts.
Whoa. So adding more targeted data literally made the model dumber about those specific facts than if you'd done nothing.
Exactly. It's catastrophic forgetting, but it's triggered by over-infusing specific knowledge. Data overload causing amnesia.
That's kind of terrifying if you're training models. You think you're helping, but you're actively hurting it. But why isn't this collapse point the same for all models? You mentioned it depends on scale.
Yes, and this is maybe the most crucial finding. The collapse point depends heavily on the model size, non-F dollar. Specifically, they found that larger models reach their peak performance and start collapsing at lower injection frequencies compared to smaller models.
Wait, hang on. Larger models collapse sooner. That seems backwards. Wouldn't a bigger brain have more room for facts?
You'd think so, right? But the paper suggests it's about efficiency. Larger models are just fundamentally more efficient at absorbing and encoding information. They have vastly more parameters, so they can represent the new knowledge more effectively with less repetition. They reach that saturation point faster.
I think I see. So because they learn the repeated facts so quickly and strongly, any further repetition becomes counterproductive. Much sooner. It's like extreme overfitting on those injected sentences.
That seems to be the idea. Continued injection past saturation forces the model to prioritize those few repeated facts so heavily that it starts overrating or interfering with other knowledge, potentially even the general knowledge learned from the main corpus. Catastrophic interference, essentially.
So the practical takeaway is, if you're moving to a much bigger model, you can't just keep the same proportion of specialized data. You actually need proportionally less frequent injections.
That's the core insight. Blindly scaling up your specialized data frequency along with model size is likely pushing you right into that collapse zone, hurting overall performance.
Which means we desperately need a way to predict where that collapse point is for a given model size without having to train it first.
Exactly, and that's what led them to develop the actual scaling law. They needed a mathematical function, a formula that could capture this whole process. The initial benefit of repetition and the eventual sharp penalty of going too far.
Okay, so what did they come up with? You mentioned P3 earlier.
Right, they tested a few functional forms, but the one that fit best, which they call P3, looks like this. PF equals a set FBF. Beat C, SP, NI, PEF. PEP is the performance metric, like that PPL-based score, and Phi dollars is the knowledge injection frequency. The $8 and $6 are just parameters you fit to the data from your experiments.
Okay, let's unpack that equation. It looks like two main parts multiplied together.
It is. The first part, a KP out FPB. That's a power law. This models the initial learning phase where performance increases as frequency dollar goes up. More repetition helps up to a point. It captures that classic diminishing returns effect.
Okay, that makes sense. That's the good part of repeating facts.
Okay.
What about the second part, the XPL?
That's the crucial addition. It's an exponential decay term. This part models the downside, the memory collapse. As the frequency dollar gets large, this term gets very small very quickly, pulling the overall performance dollar down sharply. It represents the penalty for overinfusion.
So the whole formula balances the benefit against the penalty. Clever.
Exactly. It mathematically embodies that trade-off. And the neat thing is, once you have this formula and you fit the parameters A, B, C, dol using data from, say, a smaller model, you can use calculus, just basic derivative stuff, to find the exact frequency dollars where the performance dollar is maximized. You set the derivative dt at t to 0.
Don't scare the listeners with calculus.
Okay, fair point. But the result is super simple. The optimal frequency, let's call it $5, turns out to be just $5 is BC day. A straightforward ratio of two parameters you already found.
Okay, $5 equals BC dol. That gives you the predicted best injection frequency for the specific model size and data size you ran the experiment on. That's already useful.
Yes, but the real magic is predicting this for models you haven't trained yet, especially the massive one.
Right. I don't want to run even a small 3B parameter experiment if I can help it. I want to use my tiny 137M model results to predict what will happen with a hypothetical 70B model. How do they bridge that gap?
They connect it back to other well-known scaling laws in LLMs, like the Chinchilla scaling laws, which relate model performance to compute, usually measured in FLOPs, floating point operations. They calculate the total compute cost for training, often estimated as $Z is 6 NDI, where numbers is parameters and dollars is tokens. 6 is just a constant factor commonly used.
Okay, so FLOPs basically represent the total computational effort.
Right. And they found that the optimal frequency, that 5 we just calculated, BAC itself, follows a scaling law with respect to this total compute dollars. They modeled this relationship using another power law function, 5C AC alpha plus EI. Here, $, and LLM are new parameters you fit by looking at the optimal 5 values you found across several different small model runs, different sizes or data dollars, leading to different compute dollars.
I think I get it. So, step 1. Run experiments on a few small, cheap models at different frequencies to find their individual collapse points and optimal VALO values using the P3 formula. Step 2. Plot those optimal FIVO values against the compute, FLOPs, used for each run. Step 3. Fit this second scaling law, AC alpha plus EO, to that plot.
You got it.
And now, if I want to train a giant new model that will cost a certain amount of compute $, I just plug that dollars into my second scaling law, and it spits out the predicted optimal injection frequency, $5, for that huge model.
That's exactly the workflow. It lets you extrapolate from cheap runs to predict the optimal setup for your expensive run, hopefully landing right at the peak performance without falling off the cliff.
And did it work? How well did this prediction hold up?
Remarkably well, actually. They reported an R-2 value of 0.9685 when predicting the collapse points across different model sizes using this combined approach.
Wow, an R-squared that high means the prediction is really accurate. That gives a lot of confidence.
It really does. It suggests this isn't just a fluke in one model size. It's a consistent scaling phenomenon.
Okay, so the core scaling law seems solid, but training isn't just about model size and frequency. They also look at a couple of other important factors, right? Like the total amount of training data.
Yes, they did. The initial results mostly used a 58 billion token corpus. But real-world pre-training often uses much more data. So they reran experiments using larger corpora, 75 billion and 100 billion tokens.
And what happened when they just added more general training data? Did the collapse phenomenon disappear?
No, it didn't disappear. That was a key finding. The memory collapse phenomenon persists even when you have a lot more general data in the mix. You can still overinfuse and hit that performance cliff.
Okay, but did anything change?
Yes, two main things. First, perhaps unsurprisingly, using more training tokens generally improved the model's overall knowledge retention baseline. Bigger corpus, smarter model, generally speaking.
Makes sense. And the second thing?
The collapse point shifted. With larger corpora, the peak performance and subsequent collapse occurred at higher injection frequencies.
Higher frequencies. Why would more general data let you get away with more repetition of the specialized facts?
Think about it in terms of dilution. If you inject, say, 1 million fact sentences into 58 billion tokens, those facts are relatively concentrated. But if you inject that same 1 million facts into 100 billion tokens, they're now much more spread out, more diluted by the general data.
Okay. So to get the same learning effect, To make sure the model actually sees and reinforces those specialized facts enough amidst all the other data, you need to repeat them more often.
That seems to be the logic. The increased general data means you need a higher frequency $5 for the specialized knowledge to counteract the sort of ambient forgetting or interference from the much larger volume of general tokens.
That's another really practical insight for training recipe design. Your optimal $5 depends not just on model size dollars, but also on the total corpus size dollars.
Definitely. It adds another layer to the optimization.
Okay, one last nuance they checked. Template diversity. Does it help to say the same fact in lots of different ways linguistically? Like the capital of France is Paris, Paris is the French capital, France's capital city is Paris, etc., versus just repeating one version.
Yeah, they tested this by comparing runs using just one template per fact against runs using 10 or even 100 different paraphrase templates for the same underlying knowledge triple.
What did they find? Is variety the spice of life for LLM memorization?
The results were maybe a bit surprising, especially given the effort it takes to create diverse templates. For very small models, like under 500 million parameters, they did see a small marginal benefit from using diverse templates, like maybe a couple of percentage points improvement in retention.
Okay, a tiny boost for tiny models. What about for the bigger ones, like the 3 billion parameter model?
As the model size increased, that benefit essentially vanished. The performance gain from using diverse templates became negligible or statistically insignificant compared to just repeating a single simple template.
Really? So for reasonably large models, all that effort generating paraphrases doesn't really buy you anything for factual memorization.
Apparently not, based on these results. It suggests that larger models are robust enough to generalize the underlying fact from even a single phrasing, and simple repetition is sufficient for effective memorization. Overfitting to one specific wording doesn't seem to be a major issue for them in this context.
That's actually a huge relief from an engineering perspective. Sticking to simple templates is way easier and cheaper.
It certainly simplifies that aspect of the data preparation pipeline.
Okay, let's try to wrap this all up. What's the big takeaway from this whole investigation?
I think the main contribution is providing concrete, quantitative guidelines for injecting knowledge into LLMs during pre-training. They clearly demonstrated this memory collapse phenomenon, the danger of overinfusion. And critically, they didn't just identify the problem, they provided a tool to manage it, the Knowledge Infusion Scaling Law. That combination of the P3 curve fitting and the FLO keys-based extrapolation allows you to predict the optimal infusion frequency, maximizing knowledge gain while minimizing the risk of catastrophic forgetting and wasted compute.
Yeah, it feels like it moves the process from a bit of a guessing game, maybe based on intuition, towards something much more predictive and principled. You can optimize your training recipe based on data from smaller runs.
Exactly. It's about efficiency and avoiding negative consequences.
Of course, we should mention limitations. As rigorous as this was, the models topped out at 3 billion parameters.
Right. While the scaling law showed great predictive power up to that point, the ultimate test will be validating whether these same laws hold for the truly massive, state-of-the-art models, the ones with hundreds of billions or even trillions of parameters. That's crucial future work.
Absolutely. And thinking about those massive models leads us to maybe a final provocative thought for you, our listeners. Given this paper's finding that larger models saturate their knowledge capacity and hit that collapse point with fewer relative injections, are we potentially already over-infusing specialized data in many of today's huge pre-training runs? Could it be that by trying to make models experts in certain domains, we're inadvertently pushing them past their optimal point and subtly hurting their overall generalization capabilities without even realizing it? Something to think about. Thanks for joining us for this deep dive into knowledge infusion scaling laws. We'll catch you next time on The Deep Dive.